Yay!
Yay! Okay, here's kind of a standard problem in conserving angular momentum that looks a little tricky at first, but it's really not. It's really not that tricky. Okay, here's the idea. I have a bicycle wheel oriented in some vertical plane. And then what happens is I'm going to drop this lump of mud or putty or whatever onto the wheel. And what I want to know is what's going to be the rotation rate of the wheel after it drops on. Because if I drop that thing on, after this thing falls and sticks to the wheel, it's going to start to spin, right? So let's see what the rate of spin is going to be. Okay, so here's what we do. It's not clear how we're going to do this, maybe at first, but it really does come down to momentum conservation. Here's why. So I'm going to say Li is Lf. What is the initial I omega for the wheel? This is 0, right? Because the wheel's not spinning. The wheel's just sitting there at rest. But that's angular momentum for the system. All right. So what else is happening in the system? Well, initially, the wheel's not spinning, sure enough, so that part is 0. But that mass is falling, right? And this is sort of like the first problem we did in the unit. Here's the axis I'm interested in. And I've got a mass that's moving some distance d away from that axis. And so that angular momentum of that mass about that point, we need to add into the system. And that angular momentum is, it's just going to be mvd. mvd. Okay, so that's the angular momentum of the whole system. It's got 2 parts, or at least possibly 2 parts. One of them happens to be 0. But there's 2 objects in the system, so I got to write down angular momentum for each one. And then this is going to be L final. Okay, what is L final? Well, L final is just going to be, I've got the hoop. This is a bicycle wheel, right? Which is like a hoop. So that's just going to be mr squared. And I've got this lump sitting out there, little m at the same distance r squared, right? So I'm just adding those 2 up, and this is times omega final. So there's my I final and omega final. Okay, so I think I'm all set. So what is that d? If I know the theta, I mean, maybe you're given a d in the problem. Sometimes you're given a theta, what the angle around the wheel is, this thing drops. If you're given that, then it would just be mv r cosine theta. That kind of makes sense, right? Because when theta is 90 degrees, you're coming right down on the top of it, so that's going to be 0. D is 0. And if theta is 0, you're all the way out at the edge, and so d would be equal to r, right? Cosine theta is equal to 1. So that kind of makes sense. So this is equal to mr squared plus little mr squared times omega final. So the final rate of rotation is just going to be mvr cosine theta divided by, big M r squared plus little m r squared. There we go. So if you plug in all of those numbers, what did I get? I got like 0.24 radians per second. And then if you want to put that in terms of RPM, that's how most people like to think of it. Remember what you do to go from one to the other. Roughly, I put my little squiggle there so I can do anything I want. Roughly, you just move the decimal point over, right? So that's just going to be about 2.4 revolutions per minute, something like that. Okay, so this is kind of a cool example. You usually see this expressed some way in most books. where you have something falling onto a wheel and sticking. Sometimes it's not a wheel. Sometimes that might be a merry-go-round, and you might have a kid who's running onto the merry-go-round to make it spin. But again, if you're running right at, if D is 0, if you're running right at the center of the merry-go-round, it's not going to spin, right? You're just putting a force on the merry-go-round. You have to go some distance D away from the axis in order to make the thing spin. The farther away you go from the center, the faster the thing's going to spin. So that ought to sort of make sense.